This program is intended to supplement the training given by a certified scuba instructor. While scuba diving is a safe and exciting sport, you will need to be aware of a few important considerations about how pressure, volume, and density affect your body. This video will help you to understand how science relates to scuba diving. Think of air and water with dynamic properties. Because air and water are composed of molecules, the behavior and density of those molecules will be influenced by changes in temperature, gravitational pull, volume, and density. Molecules move more slowly in colder temperatures, more quickly in warmer temperatures. As the molecules of O2 or oxygen and N2 or nitrogen move from the outer atmospheres toward Earth, they become increasingly compact. As we ascend into the atmosphere above us, where molecules are less compacted, the pressure decreases. In fact, as we ascend approximately every 18,000 feet, the pressure is cut in half. Outside of the Earth's atmosphere, say 30 miles up, air is very thin, and so is molecular density. Buckminster Fuller said that there is no up or down, only in and out. Looking at our planet, you can see how that's true. We can move towards the Earth's gravitational pull or away from it. As the molecules draw closer to the Earth's surface, they become more dense, creating more atmospheric pressure and require less space or volume. By the time this gas we call air, comprised of 78% nitrogen, 21% oxygen, and 1% other gases, reaches the Earth, this gas has a measurable pressure, volume, weight, and density. At sea level, air weighs a little less than a pound per square foot. Seawater, on the other hand, weighs about 64 pounds per cubic foot, making seawater roughly 800 times more dense than air. It's no wonder then that there's considerably more drag moving through the water compared to moving through the air, so you may feel as if you're moving in slow motion underwater. You are, after all, moving 800 times more molecules or density with your every movement underwater. Because of the molecular density differences between air and water, sound travels 4 times faster in water than in air, and light waves travel about 1/3 slower in water. And because we determine the source of a sound by the milliseconds of difference it takes the sound to reach one ear than the next, our ability to actually locate a sound source underwater is completely impaired. That's because the sound will be arriving at each ear at perceptibly the same time. Water is such a good conductant that it will rob your body's warmth 25 times faster than air. For this, we adapt using an exposure suit. Objects underwater, because of the mask and airspace between your eyes and the lens, appear 33% larger. Similarly, objects underwater appear 25% closer. So if you think you're having a close encounter of the large kind, remember, 33% larger, 25% closer. Right away you can see that there are huge sensory differences between living on land and being under the water. But this is only where the differences begin. We've adapted fairly well to living with the constant pressure of 14.7 pounds per square inch at sea level. This pressure is the result of many miles of air above us, weighing on us. We live with it and therefore, because we're adapted to it, we don't even notice it. Fish, too, live with dramatic pressure changes in their water environment as they swim up and down in the water column. But if you drive into the mountains, you'll quickly realize that there are pressure changes going on in your ears. Submerge into water as little as, say, 5 feet or so, and you'll notice pressure changes. Big difference between gaining 3,000 feet in elevation and simply descending 5 feet into water. Because science endeavors to make sense out of the world around us, it has come up with the concept of an atmosphere of measurement. The 14.7 pounds per square inch of pressure at sea level, that's an atmosphere, or 1 ATM. As we ascend in elevation, we experience less than an atmosphere of pressure. And as we descend in the water, we experience pressure greater than an atmosphere. Actually, with every 33 feet of seawater, there is an increase of 1 atmosphere. 34 feet in fresh water because it's less dense. We'll be discussing seawater to keep it simple. The accumulation of atmospheres combined with the surface atmosphere gives us a measurement in atmosphere absolute, or ATA. The greatest actual pressure gradient occurs between the surface of the water and 33 feet down. The same pressure change that happens between 33 and 99 feet. The 3 main air spaces in the body that you, as a diver, should be aware of are the sinus, middle ear, and lungs. Because they are air spaces, they will be subjected to changes in air pressure while you descend and ascend in the water column. An airspace will incur changes in pressure such that there will be twice as much pressure exerted on your middle ear, for example, between the surface and 33 feet, or 2 ATMs, and 4 times as much at 99 feet, or 4 ATMs. And conversely, as you ascend, your body experiences decreasing pressure by a factor of 4 as you surface from 99 feet. This relational phenomenon between pressure and volume is explained by a 17th century scientist named Robert Boyle. We call it Boyle's Law. There are basically 4 gas laws that have relevance in scuba diving. Boyle's Law, Charles' Law, Dalton's Law, and Henry's Law. You've held your breath and dived underwater. If you don't release your air, you come up with the same volume of air you went down with. When you're breathing compressed air underwater, your scuba equipment gives you air which is the same pressure as the surrounding water. Boyle's Law states that with any gas remaining at a constant temperature, the volume varies inversely with the absolute pressure, while the density varies directly with the absolute pressure. Or simply, when the pressure is increased, volume decreases, and conversely, when pressure decreases, volume increases. Remembering how molecules, whether gas or water, become more dense the closer they get to the Earth's core, that increased density would also equal increased pressure and a decrease in volume because the molecules are compacting themselves. And that's basically it. Imagine the molecules being packed more tightly together because of the surrounding pressure. You have increased molecular density and a decrease in volume. And on the other hand, when molecules have less pressure being exerted on them from the weight of the water and the atmosphere, they spread out, creating greater volume and less density. You can see how the principles of Boyle's Law would affect your sinuses and middle ear. And while this may seem to be an extreme condition to put the body through, there are really quite simple ways to offset the effects of pressure on the body. The Valsalva maneuver is one such way to offset pressure's effects on the middle ear and sinus, and is the most common technique. Simply block the nostrils, closing the mouth, and gently blow. The Toynbee maneuver is also used to relieve pressure in the middle ear. It's as simple as blocking the nostrils, closing the mouth, and then swallowing. Additionally, you may choose to rock your jaw or simulate a yawn. A reverse block can happen when ascending in the water column and the pressure in the middle ear builds. This is the opposite phenomenon that occurs when descending. To fix this, simply descend a few feet to the point before the pressure was felt, and then use the Valsalva or Toynbee maneuvers, then attempt the ascent again. So to recap here, when a diver is descending and pressure against the ear doesn't seem to be able to release, ascend a few feet and attempt the Valsalva or Toynbee maneuvers again. When ascending in the water column, the pressure a diver may feel in the middle ear is called a reverse block. Simply descend a few feet and attempt the Valsalva or Toynbee maneuvers. In fact, it's a good idea to even equalize at the surface of the water before even beginning your initial descent. As for the lungs, if you're always breathing, which you should be, it'll keep you relaxed and you'll avoid lung overexpansion problems. Think of a balloon. Get the picture? Your body's air spaces aren't the only ones affected by the principles of Boyle's law in scuba. There is the air bladder in your buoyancy compensator, or BC. As you descend, increasing water pressure compresses the air inside the BC. For that matter, the tiny gas bubbles in your wetsuit's neoprene as well. The decreased size of the BC bladder results in the BCs displacing a smaller volume of water, causing you to lose buoyancy. To get neutrally buoyant again, you must add air to the BC. On ascent, this air must be released. Otherwise, as the pressure decreases, the air in your BC will expand, causing you to be more buoyant and rise too quickly. Charles' law, sometimes referred to as Gay-Lussac's law, states that for any gas at a constant volume, the pressure of that gas varies directly with the ambient temperature. Or, cooling a gas decreases its volume, and heating a gas increases its volume. You would, therefore, not want to leave your air cylinder or tank in a hot car, for example. Simply, when molecules in a gas are heated, they need more room to move around, increasing the pressure in the confined space. When they are cooled, they need less room, decreasing the pressure. Typically, on a hot day, if your tank shows that it's full with a gauge pressure of 3,000 psi, when you put it in the water, being colder than the air temperature, you may notice that its pressure has dropped to, say, 2,700 psi. That's pounds per square inch. Dalton's law states that the total pressure exerted by a mixture of gases is equal to the sum of the pressures exerted by each of the gases if it alone were present and occupied the volume. Simply stated, mixed gases will stay in the same proportions under pressure. One gas in a mixture will not compress more or less than another. For us in scuba, this means our bodies will absorb the same proportions of a gas mixture, irrespective of the depth. It is this principle which makes it possible to estimate gas levels in our bodies, plan repetitive dives, and avoid the bends. You can see how this would directly impact a diver's air consumption. The compressed air that a diver breathes at depth will be used more quickly than at shallower depths. Henry's law states that the amount of gas that will absorb into a liquid at a given temperature is almost directly proportional to the partial pressure of that gas, meaning that at higher pressure, our bodies will absorb more gases. At great depths, the amount of nitrogen and other gases absorbed into our blood and tissue is greater than the amount absorbed at shallow depths. The two laws address themselves to the fact that when a diver descends in the water column, the gases he breathes will ingas or become liquid. This is because all gases are soluble in liquids. This gas exchange occurs in the tiny sac-like vessels called the alveoli. Nitrogen is a gas that is most readily absorbed into the blood and body tissues. Body tissue is roughly 80% water. When a diver ascends slowly, the gas or air will outgas back into its gaseous form and will safely be expelled from the lungs. Boyle's law, Charles' law, Dalton's law, and Henry's law all pertain directly to scuba diving. Each of them are important considerations in keeping you comfortable and safe. Certain risks are native to every sport. Scuba, because of a variety of thermal, pressure, and breathing adaptations inherent to the sport, is no exception. If the body is pushed too aggressively to adapt to a change in pressure, for example, accidents, though rare, can happen. If a diver is getting chilled or hypothermic, a diver should make plans to get out of the water as soon as possible. While suiting up on a hot day, it's easy to get hyperthermic. The easiest way around this is to fully suit up at the last minute before entering the water. As discussed previously, the body can adapt to pressure changes using the often used Valsalva or Toynbee maneuvers. They are simple and effective. Remember Boyle's law, which basically says, when pressure increases, the volume decreases. When pressure decreases, the volume increases. Seeing what happens to a balloon, the same physical law applies to the lungs if the breath is held. The cardinal rule of diving: never hold your breath. According to Boyle's law, from 2 atmospheres to the surface of the water, the air in a confined airspace doubles in volume. This is made even more dramatic given that the air being breathed at depth has greater density, which creates even greater expansion on ascent. For a diver, if the breath is held, this could result in a lung overexpansion injury. One of the most important instincts to overcome as a diver is the impulse to hold your breath. Pulmonary barotrauma is the basic term for any lung injury caused by the failure to allow expanding air to be exhaled from the lungs during a water ascent. These injuries include arterial gas embolism, air pressurized inside the lung can escape and make its way into the circulatory system. That bubble of air can occlude an artery, causing loss of consciousness or a stroke. This is an arterial gas embolism, or AGE, and the most dangerous of all diving accidents. Mediastinal emphysema. Air pressurized inside the lung can force air, if not into the bloodstream, into the mediastinum, located in the middle of the chest. This too can cause loss of consciousness. Subcutaneous emphysema. Expanding air can also travel out of the mediastinum, making its way to the area around the breastbone, creating a feeling of fullness around the neck. Pneumothorax. A lung rupture can also force air into the space between the lungs and the lining of the chest wall, or pleural space, which can potentially collapse a lung. Symptoms include severe pain and difficulty breathing. While these accidents are quite rare, you need to know about them. When you keep breathing while diving, you keep yourself safe, comfortable, and clear thinking. It's an easy and relaxing thing to do, even out of the water. Notice your breathing. Long, slow, and deep breaths relax us and affect much clearer thinking and reasoning abilities. Dalton's and Henry's laws both refer to how air, or any gas for that matter, is affected by pressure. When we dive underwater, nitrogen and oxygen diffuse, or in-gas, into our blood and tissue. When we ascend, the oxygen and nitrogen come out of solution, or outgas from our blood and tissues. Decompression sickness. Decompression sickness, or DCS, occurs simply when the gases that we in-gas at depth outgas too quickly on ascent. This rapid form of outgassing creates gas bubbles in the tissues or blood before it's able to diffuse into the lungs and be eliminated by our out breath. The symptoms may appear immediately after a dive or up to a few days afterwards. The symptoms include weakness, joint pain, skin rash, numbness, tingling, and paralysis. Factors that may increase the chances of DCS include lack of sleep, alcohol, dehydration, illness, age, cold water, exhaustion, or gaining in altitude after a dive. DCS can be extremely dangerous because it can cause permanent injury. If DCS is suspected, a diver must breathe pure oxygen and be transported to the nearest recompression chamber. Oxygen provider training is available through several agencies. The recompression chamber will reduce or eliminate the symptoms. After recompression, and the gases go back into solution, the patient is then decompressed, allowing the gases to slowly come out of solution this time. Nitrogen narcosis. Scientists don't know the exact cause of nitrogen narcosis, but occasionally, at depths of around 100 feet, the increased nitrogen in the body can produce, among other symptoms, a euphoric sensation. Although the sensation is not an alarming sign, the way it can impair one's judgment, reasoning, and ability to perform simple tasks can create dangerous scenarios for the diver. By simply ascending a few feet, the effects can completely disappear. Most of all dangerous situations can be avoided with a few simple rules. Keep breathing. Never ascend faster than 30 feet per minute. Keep within your non-decompression dive limits. Stay hydrated and stay with your buddy. Taking dive specialty courses like altitude diving, advanced diving, wreck diving, and so on will make you a better, safer diver for your buddies and for the marine environment. It's so simple to be safe. Diving offers such an exciting underwater universe to be discovered. But knowing what can happen and how to avoid it will increase your pleasure and confidence as a diver.